Hello everyone, and welcome back to the Exam SRM YouTube series. In today's lesson, we are covering the topic of k-means clustering, particularly as it relates to the Society of Actuaries Statistics for Risk Modeling exam. By the end of this video, you will understand how k-means clustering works, how the algorithm iterates toward a solution, how to measure within cluster variation, and considerations for k-means clustering. Let's get started. Suppose we have 40 individuals, with each individual represented as a point in this two-dimensional plot. The x-axis represents annual ER visits, and the y-axis tracks body mass index. We want to organize this data into meaningful groups, since it's not obvious from looking at the raw data. How can we do this? This is where k-means clustering comes in. The k-means clustering algorithm helps us group data points by how similar they are to each other. We'll walk through the step-by-step process later in the video. And since visuals are helpful for this topic, we'll lean heavily on them throughout the video. Before we cover the algorithm, let's see what the final results look like for different values of k. Here's k equals 2, k equals 3, and k equals 4. Note that we need to determine the number of clusters k before running the algorithm. We'll cover this later in the video. Before diving into the algorithm, note that k-means clustering is an unsupervised learning method. This means that the model's goal is to infer the natural structure of the data without prior knowledge of the data's classifications, meaning the data is unlabeled. In unsupervised learning, the algorithm only uses the feature space to form clusters and does not use a separate response variable as a target. For example, outcomes like claim cost are not shown to the algorithm when it creates the clusters. After clustering, we can bring in a response variable separately, not to form the clusters, but to evaluate or interpret them based on the final clusters. Here, we show the general procedure for the k-means clustering algorithm. In step 1, we begin by randomly assigning each observation to one of the k clusters. This gives us our initial cluster assignments. Next, in step 2, we compute the centroid of each cluster and assign each observation to the cluster whose centroid is closest. We repeat this process until the cluster assignments stop changing. Feel free to pause the video and think about how this works before we move on to an example. Let's walk through a k-means clustering example with 40 random data points. We have 40 randomly generated data points, and we'll cluster them into k equals 4 groups. We begin with 40 unassigned data points, and we'll organize them into 4 clusters. Step 1. We randomly assign each observation to one of the k clusters. This gives us our initial cluster assignments. Step 2, Part A. For each of the 4 clusters, we compute the centroid, which is the average position of all points in that cluster. In two-dimensional space, the centroid's x value is the mean of the x coordinates in the cluster. Similarly, the centroid's y value is the mean of the y coordinates in the cluster. Step 2, Part B. We now reassign each observation to the closest centroid based on Euclidean distance. Let's look at an example. We calculate the Euclidean distance from this point to each of the 4 centroids. The Euclidean distance is the straight line distance between 2 points. It's calculated using the square root of the sum of squared differences across each coordinate. The distance to cluster 2 is 21.82, which is less than the distance to all other clusters, including its current cluster. Therefore, the point is reassigned to cluster 2. This process is repeated for all points. We repeat the centroid calculation and point reassignment using the new centroids until the cluster assignments stop changing. The algorithm converged in 10 iterations, successfully grouping the 40 points into 4 distinct clusters. And that's it, we're done. Now that we've seen how k-means clustering works, how do we determine if the clusters are good? The most common way is to calculate the within cluster variation. This variation measures how similar the points inside a cluster are. Using the standard measure based on squared Euclidean distance, the within-cluster variation for one cluster CK is given by the formula you see on the screen. The cardinality of CK is the number of observations in cluster CK, and Xij is the jth feature of observation I. So in our previous example, where p equals 2, xi1 is the x-coordinate value, and xi2 is the y-coordinate value for observation I. Let's try to conceptualize what this formula means. The summation part of the formula takes every combination of points inside the cluster, labeled I and I prime. For each pair and feature, we measure the squared difference, so bigger gaps count more than smaller ones. This formula is essentially the sum of the squared Euclidean distance between every pair of points in the cluster. After completing the calculation for all features and all pairs, we get the total variation for the points in cluster K. We then divide by the number of observations in the cluster to get a more standardized measure. You may notice that the within-cluster variation formula looks similar to the mean squared error formula. Both formulas rely on minimizing the sum of squared differences. Although the two formulas have different inputs, the idea that large differences get penalized heavily works the same way. After we calculate the within-cluster variation for all K clusters, our optimization criteria is to find the clusters that minimize the total within-cluster variation for all clusters. I hope this video has helped you understand the concept of within-cluster variation. Before we move on to the final section, if you found this video helpful, please drop a like and subscribe for more videos like this. And if you know anyone who might benefit from this video, please share it with them. While K-means clustering is a powerful, unsupervised learning technique, there are several important considerations to keep in mind when applying it. Let's walk through some of the key factors to remember for the exam. K-means usually converges in a reasonable number of iterations. However, it may settle at a local minimum rather than the lowest possible global minimum based on the within-cluster variation we just discussed. The standard workflow is to run the algorithm several times with different random starting points, then pick the run that gives you the lowest within-cluster variation. Let's run the K-means clustering algorithm 6 times on the same data with different random starting points. Notice how different initializations can lead to different results. Even though we're using the same data every time, different starting positions lead to different final cluster assignments. That's why we should run K-means multiple times and pick the cluster with the lowest within-cluster variation. Another issue with K-means clustering is standardization. When variables exist on different scales, you may need to rescale them so they contribute more evenly to the distance calculations. Moving on to the next bullet. A common challenge with K-means clustering is deciding how many clusters to use. This is done before you run the algorithm. The algorithm cannot determine this for you, so judgment and diagnostic tools are needed. Okay, so what do I mean by different initializations leading to different results? Let's look at the same 40 data points clustered with k equals 3 versus k equals 4. Even though both results are valid based on the K-means clustering algorithm, it's not immediately clear which one better represents the true structure of the data. The number of clusters is a decision you have to make before you run the algorithm. The algorithm cannot decide for you. There are methods that can help you decide, but they are beyond the scope of this exam. It is also important to remember that clustering always produces clusters. In some cases, the groups you see may simply reflect noise rather than true subpopulations. There are methods that try to assign p-values to clusters, but there is no widely accepted best approach. Clustering can be sensitive to small changes. Removing a few observations or slightly altering the data can lead to different cluster assignments. This is why interpreting clusters should be done carefully. Let's see what happens when we remove just a few data points using the same initializations. Here's the final clustering result with all 40 points versus the result with only 36 points. Notice how running the algorithm with 4 observations removed can shift the centroid positions and change some of the cluster assignments. This sensitivity to small changes is why you should be cautious when interpreting clustering results, especially if your dataset is small or your clusters aren't well separated. Finally, clustering forces every observation into a group, which can cause distortion when outliers are present. Mixture models offer a more flexible alternative because they allow points to belong to multiple clusters to varying degrees. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.